Different frames of reference will have a different perspective on when and where events take place. They'll have a different set of space and time coordinate values for any given event that we are considering. And that is one of the beauties of the special theory of relativity, to go from the location and time that one person says something happens to the location and time that another person says that they happen. Now, that being the case, it is often useful to have quantities that everyone agrees on. They provide, if you will, a kind of anchor. They provide quantities that transcend the differences between different perspectives. So it's useful to find what we call invariants. So invariants are those combinations of coordinates that do not vary from one frame of reference to another. That's what I'd like to derive for you, some space-time coordinate invariants. To do that, I'm going to break the discussion up into a couple of pieces. I'm going to start where things are more familiar, invariants of just spatial coordinates. And after we cover that material, which is probably totally familiar to you, we will generalize to the case where time is part of the story too. Okay, let's begin with a familiar example. Let's imagine that we have two grids, and I'm going to use the grids that I've introduced earlier. They're going to have a common origin. Let's be concrete. Put that origin, say, at the Empire State Building. And we are going to look at the fact that the Chrysler Building has different coordinate values in the different coordinate systems. And then we're going to try to use those coordinate values to find what it is that the two coordinate systems agree on. Okay, so here's coordinate system 1. There's coordinate system number 2. If we, again, pull these guys apart, Chrysler Building has coordinates 4, -3 in one system, coordinate 5, 0 in the other. But as no doubt you know, there is a combination of those coordinates that everybody will agree on. All we need to do is consider the sum of the squares of the coordinates in each system. So just by way of review, let's do that. So for the Empire State Building, it's at 0, 0 in both systems. Chrysler's at 4, -3 in the red system. It's at 5, 0 in the green system. And now if we look at the sum of the squares of those coordinate differences, we'll get 4 squared plus -3 squared is 25 in the red system. We'll get 5 squared plus 0 squared equals 25 in the green system. And they agree. Now, why do they agree? We all know why they agree. We're talking about, with that particular combination of coordinates, if I take the square root of that number, I'm talking about the distance between these two locations. And the distance between here and here doesn't care about the coordinate system that you might happen to use. The distance doesn't change when you start rotating coordinates. It's just the coordinate labels that change. And this particular combination of the coordinate labels is, by the Pythagorean theorem, the distance between these two locations in either system. And therefore, that number has to agree because distance is a coordinate invariant. Doesn't care about the coordinates that you use. Okay, so that's a familiar idea. Let's just make certain that we're all on the same page by fiddling around with a little demonstration. And this demonstration, you get to choose the angle between the two coordinate systems, and you get to pick the location of the point of interest. So that's the yellow dot. And the thing that I want you to take away from this demonstration is that if you look at this number as I vary the angle, the coordinate values will change, but the sum of the squares will not. So here we go. Notice that the numbers are all changing, but 127 in this particular case is fixed because that is the distance of that point from the origin, and the distance doesn't care about the coordinates that you use. So this is a good model for thinking about invariance of a coordinate system. We're now going to jump off from this example to put time into the story and look for invariance of space-time coordinate systems.